Okay, before I get into this example, which I have here, and I'm going to go back and I actually, well, I'll just leave these in here because I already did this and spent 25 minutes or so, and I forgot to hit record. So I'm going to just kind of go back over this again here real quick. Um, the Let me see if I get this out of here. Sorry about this. Okay. So if I before I go over that example here, what I want to do is I want to show you that when we went through this scenario here, we basically set up by simulating uh, this particular basketball player. If you remember this from last class, going over and having an 80% free throw average and shooting 50 foul shots, recording the percentage, shooting 50 foul shots, record the percentage again, and repeat that 1,000 times. And we saw that we had this pattern here. And this, again, is a computer simulation here of what an 80% free throw shooter would do over the long haul. And but this particular one here shot 32 out of 64. So the computer simulation was only, again, the 7 times out of 1,000. Our probability model, which was a normal one, and that's kind of why I'm going over this again, is that we saw that these things followed a normal pattern here. And so this probability here was pretty close to the actual results that we got here during the simulation. Okay. So all of this really, let me just get this out of here now. I don't need that anymore. Set up this scenario here. This is just summarizing here, stating that, you know what, different set of hypotheses here, but if it's 0.9, we're going to say that the distribution of all these sample proportions here. So when I actually did do it, let's say if it was a 90% free thrower and they made 86% here of their free throws, that these are going to follow a pattern of the mean is going to be the true percentage, and standard deviation is going to be the square root of p times 1 minus p over the sample size, which was about 0.03. Okay. And we did that development back here and did all that. And I don't want to repeat that, but where we're moving with this is now we want to look at, we're going to be collecting data that's numerical. So we're going to want to know what the distribution of this X bar is, or the sample mean. And what we're going to say is that it is also normal, and the mean of all these X bars are going to be the mean of the population, and the standard deviation is going to be sigma, okay, which is the standard deviation of the population divided by the sample size. Okay, so that would be the standard deviation of the distribution of these things. And then we're going to be able to use this probability model to find the likelihood of getting the results that we did for our experiment back here, which we're going to take a look at here in a second, based on the fact that the null hypothesis is true. Okay, so let me get into that one then. So like I said, I already filled these in here, so I apologize for that. But I wanted this particular example because it's a two-tailed test, and there's a issue, or maybe an issue, or a little bit of work. I don't even know if it's an issue, but a little bit of work you're going to have to do with the Excel sheet to find the p-value. Okay. So this scenario here again talks about the sodium level for healthy adults, and they're claiming that the true mean is 143, whatever that unit is per liter of blood. And so now what we're saying is that they felt that changed due to modern dietary habits, that it actually is going to be different. Now, because they use the word different here, is we're going to have to, again, just like we did with the proportions, say that it is not equal. So we don't have p anymore. We have mu, which is a mean of the population. That's just the Greek letter mu. And there's our hypothesized value. And again, the differs tells us it's not equal. And I just said over here, this distribution is going to be a normal distribution. Okay. So just to kind of hit home on that a little bit, what I did is, set up this simulation here also. And, if I had just this population here, and there's no way I can switch this over to match our scenario, but this is just locked in at 10 and 2. But if I select a sample of 30 out of there, that's what this computer's doing here. We found a mean of 9.684. We plot that down here. I can do that again and get a different 30. We would get slightly different results, which is we do here, but they're pretty close. And then I'm just going to keep kind of going here. So that's 4, 5, 6, 7, 8, 9, 10. So I got 10 samples here. You can see that the pattern here, the means are, right around 10, but obviously the individual samples, we've got some variance going on here. Okay, but on average, this is what we're getting. So, if I do that over the long haul here, it's just like what I did with the, get a nice even number of like 1,000 samples. You can see here that that pattern is, we have about an average of pretty close to 10, right? So that would be the mean of the population. And the standard deviation is 0.355 for this 1,000 X bars. So theoretically, according to what we should get over here, it should be equal to 2 divided by the square root of 30. So I think I did that on the calculator back here. If I take, go up here, because I did this, I told you I did this without the record button on. So good news is I don't have to type all this in again. But if I took 2 divided by 30, all this calculator is doing is rationalizing that denominator. So this number is the same as that. Okay, this is the same as that. And if I approximate, I should get 0.365. Okay, and over here, just with 1,000 in my simulation, I'm getting 0.355. So you can see that I'm pretty close. Now, the number of possible combinations of 30 we can get out of this super large population, which is like, for all practical purposes, is infinite, like millions upon millions upon millions of observations in here in this population. This is just a small number of those. Okay, so if we had every possible combination, which is too big of a number to count, then it would be exactly 0.365, whatever that is, the 2 divided by the square root of 30. Okay, so all that's doing is just verifying that this sampling distribution is what it is. Now, this is just, again, a different scenario here. We'll get back into that later. Okay, but I just wanted to look at this for that particular thing. So if I get back into my sample here, then, so I know it's normal. It follows the sampling distribution of 143 as a mean. The standard deviation is going to be, in this case, 15 divided by the square root of 50, okay? And I think I did that back here, actually, if I kind of scroll down here now a little bit. No, I did not. Okay. So that is going to be, what did we say it was, 15 divided by the square root of 50. Okay. So if I do take the 15 and divide by the square root of 30, that's going to give me that. And remember, this number over here is same as this. It's just performing that rationalizing the denominator. So I am going to approximate this expression right here, which turns out to be approximately that is not the right number because it should be 15 divided by the square root of 50. Try this one more time here. Apologize for that. Okay, so now if I approximate that, okay, 2.12132. Okay, so I'm going to go in here now for my normal, and notice I told you I did this already, 2.1 or 2.12132. I put that in there for my standard deviation. And all that is, again, is the 15 divided by the square root of 50. That's this distribution here, okay? So if I come over here to 139 and go to the left of that, that will give me that area or probability of getting that or less. But since the alternative is not equals, I also have to go as far in to the right, which is to the right of 147. Now, I can always get this total area right here, which is 0.0593, by just doubling this number. Okay, so if I just multiply that by 2, I'm going to get this, or I find it over here, it's going to match that because these are equidistant, right? 143 is in the middle of 139 and 147. And this is, again, was our results, but again, the not equals, I have to consider values in that direction also. So with that said, then that p-value is 0.0593, okay? So I went ahead and put that in here. Now I'm going to show you how to get this off your template, but notice there's the z value is also computed back here at negative 1.866. And so all that's doing is, again, is just saying, well, you know, prior to, having software, we had to use the table for the standard normal distribution. And so the area to the left of negative 1.886 and to the right of 1.866, which corresponds with this 147, is going to be the same as this area. And I don't want to go through all that because you did that probably earlier in the class, or the course, I should say. But I'm going to get into what does your template do. So if I go into that and I put the 139 in here and the 143 for my hypothesized value, 50, 15, just like I did, and now the significance level was 0.01. This is where there's kind of somewhat of a, I don't know, just a little bit of a rub here because it's not reporting a left tail. So as far as I know, I didn't manipulate this, so I'm not sure what's going on with this spreadsheet here, because most of the other ones here that we use, like for instance, when we did our proportion, it gives both the left and the right tail. Okay, this one for some reason is only giving the right tail. Okay, so when I'm, how do you get the p-value out of here? Well, remember, this is the area to the right of that z value. Okay, so to get the left tail, I would have to subtract this from 1 and then multiply by 2 because it's a two-tail test. So if I subtract this from 1, get that number, and then that number is actually going to be this, okay? So maybe I could just do another normal here. Let me just, what's that? 1.886, okay. So if I come over here to mean 0, standard deviation 1, that's our standard normal, plot it. And I'm going to go outside the region, 1.86 and 1.86. There is the 0.0593. Okay. So what you're doing on your spreadsheet is it's giving you the area from here all the way down here. That is that 0.97. Okay. So it's only giving you the right tail, so to speak. So that would be from here all the way over, including all this stuff here. Okay. So you would have to take this area, that's the 0.97, subtract it from 1 to get this value, and then multiply it by 2. And that would ultimately give you the p-value. Okay, so your master sheet is giving you the p-value or the z statistic. It's not directly giving you the p-value for a right tail test, or I'm sorry, for a left tail test or a two-tail test. Okay, so you've got a little bit of work to do here. If you have a two-sided test like we do here, or even a less than. Okay, the less than, you would just get it by subtracting the right tail area. So I could have picked a new example here when I didn't hit the record button, but I wanted to make sure we did a not equals here. So So anyway, that one is correct. Um, I'm going to wrap this one up because I want to try to break these videos up into the types of problems. So, but before I do that, I do want to address the idea of this type 1 and type 2 error. Okay, so the type 1 error is, no, I pull this out of here. I just want to drag this up here actually at the same time. Okay, so the type 1 error would be if the null is true. Let's say the true mean is 143 and I reject this. Well, obviously I don't want to reject it. If it's true, that's an error, right? I want to fail to reject it, which would be the correct decision. Okay, so let's just suppose this is true. Well, the probability of me doing that, and I don't know what problems you're going to get with, I just want to explain what the types of errors are that we can make, is rejecting this when we shouldn't, right? We do have control over that by picking our alpha, right? Because we said, hey, we're definitely going to reject if it's 1% or lower. All right. And so therefore we would, go ahead and do that, but the chance of that happening is pretty small, right? It's 1% or less. So, we kind of have that subjective ability to, select that, the probability of making this type of error. We got to look at it in the context of the problem is, well, hey, the true mean is 143. We're saying it's now different. What are some of the consequences? Well, maybe we put the person on one of these modern diets. Well, is it going to be harmful to them? Probably not. Okay, most likely not. But there could be something like if we did reject it, we would start medicating these people, and if that's the case and the medication has some side effects, we wouldn't want to expose them to medicine, or why medicate them when you don't need to. Okay, so because it's there's really not a point, or like I said, not a need to do that. So this would kind of vary the probability, what are the consequences of rejecting the null when in fact it's true. On the flip side of that is if it is not true, that is it truly is different, and we fail to reject it. Okay, in other words, the null is false and we don't reject it. Well, then again, if we go back to this and say, hey, we're saying 143, they're good, but really, if we should be medicating them, right, we should be rejecting and medicating them. That consequence could be dire here. Okay, but in this one here, like I said, we would just, say, well, we would be, I guess, withholding that new diet from them, and does that have a disastrous consequence? That's debatable. So, that's part of it, is like, what are the consequences of making these errors? We can always have control over this by just selecting the appropriate alpha. What risk are we willing to take for that? Whereas over here, this type 2 error, the computation of that's a little bit, the probability of that occurring is a little bit more complex, but I can tell you that the remedy of that is to just increase the sample size, and that will you'll start seeing this probability of this getting lower and lower and lower. And the complement of that would be, again, rejecting it when you should, and we want this probability high. And these two probabilities are complementary to one another. And so increasing that sample size would increase that probability of rejecting when we should. Okay, which again, that's called power. Okay, but like I said, I don't think that you're going to encounter that in this course. So, all right, so I'm going to wrap this video up here, and then I'm going to come back with the T test. I'm not going to do, I set this up. I'm not going to do one with the critical value method, because I did some of those for the Z test. And I'm going to do one of these for also the T test. So I'll do a problem like that with the next one, and they're very similar. Okay, so you'll see that when I get back into it. So, all right, so that's this video, and I'll be back with the next.